So, okay. Well, good morning, everybody, for the last day of this course. I hope you are still alive, because I think it has been a tough course. It's always a tough course, but you have to be aware of the fact that you are lucky because you only had it in half a day instead of a full day. And just imagine that you have a full day with me throwing all this information to you. Okay, let's go over the exercises. And of course, as usual, the floor is yours. So the first exercise is which of the three structures drawn will give the spectrum shown?
So I don't know, maybe I can start.
That's okay.
Can you hear me well?
I can hear you well. Okay,
good. That's good enough. So there are three candidate structures, and what I noticed first about the spectra is that M over Z 146, 188, and 230, of course, actually have the chlorine included. So I can assume that all these, for all these fragments, basically the main ring with the chlorine is kept. And for the 104, 110, I don't see this isotope, the second isotope, also 152. In that case, I assume that in these cases, the chlorine might have already left. So this is one thing. And then there is the difference between 230 and 188, that is 42. It corresponds with a C3H6 neutral loss. So, and I see that it's actually symmetric. There's also 84. So in that case, I focus on the second structure, propazine, in the middle, because it has these symmetric moieties on both sides of the ring, which can explain these symmetric neutral losses. And then what else? There is another 42 difference between 146 and 104, I think, which corresponds with, I don't know.
Well, in fact, from the story you told so far, basically having the 42 loss between the 230 and the 188, you can already conclude that it must be the propazine, the one in the middle.
Yes.
Because for the sebutylazine and the terbutylazine, you actually will see the loss of 56.
Yes, that was my conclusion as well.
Exactly. And there's one small remark which I have to make, and that is, you say in the 104 we don't see the chlorine, but actually at 106 you can see the chlorine isotope, because in the 104 the chlorine is still present.
I should change my glasses.
Yeah, well, it's a very small one, but it's there, and I know it's there because I know the identity of the ion. And we will come back. We will come back to this spectrum later on today. So then we go and have a look at it in more detail. But your story is nice. Propazine is the right compound. Yep.
Thanks.
Okay. And as you can see in my next page, in the sebutylazine and terbutylazine, you see the loss of 56, and it's actually quite difficult to discriminate from the MSMS spectra between the sebutylazine and the terbutylazine, but we can do the discrimination by LC retention time, because they show a different retention in under normal LC conditions. So that's the possibility which we have. Any questions? If not, we move to the next one. Anyone?
May I?
Yeah, please, Anna.
Okay. I think that the first cleavage that we have, it happened between N and carbon, and it gives
At the left or
us
at the right?
right.
At the right. So this.
Yes,
Yeah.
yes.
Okay.
I suppose it's give us a fragment with mass 170.
Yeah. That's this.
Yes. After that, we have a loss of water, and we have a fragment with mass 152. After that, this fragment, in this fragment, we have loss of ammonium, and we have fragment 135. After that, I suppose this fragment lost of HCCH2, and we have fragment 107, I suppose.
Okay. I think I would approach the exercise in a slightly different way.
Okay.
If you don't mind, because actually what I would expect to have cleavage on either side of the nitrogen with possibly charge retention on either side. So if I would cleave at the right hand side of the nitrogen as you proposed, I will be able to explain the 170 and the 135. And these are complementary ions adding up to 305 and plus H plus 1. Yeah. In addition, we can have cleavage at the other side of the nitrogen, where we get the 153 and the 152. Well, the 153 we don't see, but we see a 152. So it could be a possibility. And then we can also say we have secondary fragmentation. So we can have a water loss from the 153 to explain the 135. And we can have a water loss from the 170, as you proposed, to have the 152. And then the 107, I have the arrow here, but I actually think the arrow should be there because that would be the benzylic cleavage, so to say, at the tertiary leading to the hydroxy benzylic ion. Yeah, so that's basically what we have. And so we have two possible structure proposals for the 135, two for the 152, which was something which I asked for in the exercise. If we now go to the spectrum and get accurate mass, there's something interesting showing up. Because if you have a look at the accurate mass spectra, you will be able to see that all the ions explained from cleavage at the right-hand side of the nitrogen are actually observed. Whereas none of the ions related to the cleavage at the left-hand side of the nitrogen are observed. Yeah, and so all these ions are not there, and the two ions with 135 and the two ions with 152, which we proposed, have different elemental composition, so they have different accurate mass, and it's something that you can see from the values I have. So in fact, I think what we actually have here is a basically a competition between cleavage at this side of the nitrogen and the water loss, because it has been demonstrated for structures like these, and we will see this example in one of the next exercises, that the water loss is actually not a 1,2 elimination, but a 1,3 elimination. So it takes the hydrogen from the nitrogen. And that means that you will have a 3-membered ring here, which blocks the cleavage at this side. Yeah. So interpretation is okay. there are some additional details in the spectrum, and I would say that's the reason why the spectrum is there as an exercise.
And you think that my explanation about lost ammonium, it's unreal?
Of course, you can say that from the 170, you say I see the water loss, so I get this one, and I would have the loss of ammonia from there, which basically would mean that the ion you get is this.
Yes.
And that's is not observed.
Okay.
Yeah.
Yes.
And and basically if you say I get so a fragment due to the cleavage at one side of the nitrogen, and then I say I get a ammonia loss, then basically I say what you do is you cut at the other side of the nitrogen.
Mm-hmm.
Yeah.
Okay. Thank you.
So I have a general question about the MSMS fragments and what you call the accurate mass. So how accurate do you expect the MSMS mass to be in order to be usable? Because it's quite a critical point. If you compromise too much the mass accuracy, then all your the chemical formula calculations will not be accurate enough to actually make a conclusion. So
If properly calibrated, current instrumentation allows you to get accurate mass values with the error in the third decimal place or better. And that means that with values like that, and typically you have a mass accuracy better than 3 millidalton. And then if you start working out from a known structure, you get a limited number of possible elemental compositions. Quite often you only get 1 or 2, and then from having the structure, you can immediately say it can only be this one, because in order to get the other one, I would have to rebuild the molecule completely. And that is something which will not happen. So in most cases, when you are in the 3 millidalton range or below, for small molecules, that's sufficient to be certain about the elemental composition. And then, of course, it's a matter of dealing with that and doing a structure proposal based on what we have.
Yes. So in case you get 1 or 2 candidates, I understand. But let's say you use the elemental composition software and you get 10 candidates for this, mass designated mass accuracy. In that case, do you give up on this fragment and move on to maybe a lower mass fragment, or try to?
No, I will, because if you get the 10 candidates, you will not have 10 candidates with elemental compositions which can actually be made from the structure you're looking at.
I guess so, but then it starts to be a combinatorial game, So I mean,
no, because we are not playing a combinatorial game; we are playing chemistry.
Yeah, but God is playing.
And that means that we cannot have the situation that we have to take part of this and part of this and glue it together to explain a fragment. So the product ions which you see in the MSMS spectrum must have a logical relation with the initial structure. And that means the other way around, it will work the same. But of course, if you would say, I have this and I don't have the structure, I have an unknown, then it might be actually pretty difficult to come out with this structure. Especially if you would also like to be certain about, for instance, the positions of the hydroxyls on the ring, because that's something which we cannot sort out by mass spectrometry.
No. Okay, thanks.
And of course, the number of hits you get in the elemental composition calculation depends on the number of elements you have to consider as possibly being present. So it is wise to always think carefully, would it be likely that this particular element is there or not? And in some cases, what I do for unknowns is actually start out with a large number of possibilities. Then I actually get a number of hits for the precursor ion, and then I start trying to do similar calculations for the product ions, which basically in most cases will reduce the number of possible hits for the precursor ion. And I will actually show you an example of that. I think, yes, when we come to the last session of the course. Yeah. Okay, let's.
Sorry, if I may, just small question. Can you hear me? Sorry.
Yeah, I can hear you.
Yeah. So you say about the accuracy. So you say it's about if it's calibrate right until the first decimal, right? You can get.
No, in the third decimal.
Yeah, the third.
Yeah.
But the problem when we do metabolomics, when we have thousands of compounds, we never achieve it. I don't know. Maybe we do when you do, very small number of molecules, but when we get really untargeted, we get it to the second normally maximum. The question if it's common that we can.
No. If you work on an orbit trap,
yeah,
or with a modern QTOF, you should be able to get it, let's say, within 3 millidalton.
Yeah. Okay. Thank you. Yeah.
And if not, then you have to talk to the instrument manufacturer, because then there's something wrong with the instrument.
Okay. Thank you.
But of course, calibration of the M/Z axis is important. That's for sure. Okay, let's move to number 3. Anyone?
Maybe I can try again. Nobody taking the chance. So here in this structure, what I noticed on the spectra is that fragments 286 and 268 actually correspond with the nitrogen rule. And that means that the nitrogens should still be there on the structure, whereas all the other ones are uneven. In that case, the nitrogen is already gone. So,
yeah, which still doesn't give any effect on the nitrogen rule, because the nitrogen rule is still valid. But I understand what you mean. Yeah. Okay. So,
yeah, the rule is valid. Just it means that basically I can assume that there is no nitrogen on these uneven numbers. Then basically, okay, so 286 can be, so I was not completely sure, that's why, but I went ahead nevertheless. So it can be 286 can be a loss of C2H2O, basically on the ester bond.
yeah.
Yeah, here.
Yeah, and you have hydrogen rearrangement, so you lose the ethanol. Okay.
And then basically 268 then is another loss of water from 286. This water can be either the remaining hydroxyl on this what used to be the ester, or the other one on the other side.
But it can also go in one step as being the loss of the acetic acid.
Mm-hmm.
Yeah, and I can assure you the water loss is coming from this position.
What makes you
Because
so sure?
the loss of the water from the aliphatic side is far more likely than from the aromatic side.
Okay, fair enough. So that's good. So we are left basically with whatever the structure is called, with the nitrogen, and then 211 is the loss of the nitrogen containing ring. Basically from 268, C3H7N is lost. It's a loss
That's
of
57. Yeah.
And then it's kind of sequential. 193 is the loss of water from 211. Then there is basically two symmetric pairs of fragments, namely 183 and 165, that are losses of 28 from 211 and 193 correspondingly. But I'm not sure exactly what is this 28 neutral loss. It can be like carbon oxide, but or maybe C2H4, but this I could not explain.
Okay. Okay. Well, I have a scheme, and again, of course, there is accurate M/Z data, so elemental compositions underlying this. So we have the loss of either the ethanol or the acetic acid, and when you have the loss of the acetic acid, and you would write the resulting fragment as a protonated molecule, you will put an additional double bond in the ring. And then we see the loss of the, what you said, C3H7N, so the nitrogen ring, which basically means that you put another double bond in the ring if you want to continue writing this as a protonated molecule. And then for the low-end fragments, you see the loss of water, which actually comes from this side, and I have some evidence from labeled substances for that. So that's what we have, and it can show losses of CO. Alternatively, it can show loss of CO followed by the loss of water. So basically, you have the two possibilities, and you don't know whether it's going like this or whether it's going like this or whatever way it goes. Then you basically should start out with this structure and find out what is really going on, and so on and so forth. But for me, the most important step in the procedure was the loss of the nitrogen ring in the procedure. And you may have seen in the spectra that I left out some ions because there's some more things going on, but I didn't want to dig into that.
I have two corresponding questions. One is that in this case of ambiguity about the sequence of fragmentation or the most possible route, will an ion trap and the fragmentation, MS to the N fragmentation, will actually be able to resolve this conflict, this ambiguity?
My honest answer would be I don't know, because sometimes the ion trap gives beautiful results in that, but sometimes it doesn't work. So it does not give the. I don't have an ion trap spectrum of this compound available, so I can't tell whether you actually see the same fragments as we have here, and that has all to do with the energy you put in the structure, and especially if you start doing ms to the power n, so the higher rates of MS, you sometimes see fragmentation which you will not see in the collision cell CRD. Simply because if you start fragmenting a fragment, you are doing basically something different than if you have the sequence of losses which you get in the collision cell CRD.
Okay, the other question I have is that we work extensively with DIA, and obviously we get a lot of fragments that we cannot explain in the spectra. Since you already also in this case, you left some fragments unaccounted for. What do you have some kind of estimation about the number of the percentage of explained spectra that we can, let's say, upon which we can be sure that we somehow interpreted the right structure? Not even to the last detail, but at least get.
I don't think this is something which you can do. I should let me point out that actually I have explanations for all the other ions which are there. At least I have elemental composition, and in some cases I can do structure proposals, but I decided to leave them out because it will be too complex for the exercise which we have. Yeah, so that's something, and it's extremely difficult to answer your question. So what percentage of is there? And that's always difficult because that will depend on the structure, it depends on the type of compound, and so on and so forth, and the quality of the data. In principle, I dare to say that I'm less optimistic than many others in our ability to identify unknowns, real unknowns, I mean. And there are quite a lot of people who think that this is something which we can solve by software and so on and so forth. I'm curious to see whether that will actually happen for small molecules. And until recently, until last year, I always said I'm still young, so I have plenty of time to explore, but I will stop exploring soon. Okay, so let's move on now to number 4. Somebody else who would like to talk us through?
I can try.
Please.
Okay, so 242 is loss of water from OH group. 218 is a loss of C3 from the right of the nitrogen. We have two small 201 to the right from 200. This is cleavage of CN bond to the left of N, and charge is, nitrogen is going as neutral loss, and charge is remaining to the left part of the molecule. Problem with 200, I suggested that maybe it's radical because I have no other explanation. Maybe it's some rearrangement, I didn't check it, but sometimes I know that we can have radicals, so it is loss of another proton. H, and 200 is just radical. And 183 is 201 minus water. Minus
Okay.
OH group. So
Okay.
my problem with 200, if you can explain, would be nice.
Yeah, well, I will do so, because I think from the many people who worked on this exercise in these courses, you are the first, really the first, to notice the 201. And I like that, because I think the 201 is an important ion. So what most people do is they say what we see is we see the loss of water to the 242, we see the loss of propene to the 218, and then we have the loss of water from the 218 to the 200, and then we have the loss of ammonia to the 183.
Okay.
Yeah, that's what most people do. And in fact, it has been demonstrated that the water loss is not a 1-2, but a 1-3 elimination. So the structure proposal for the 242 would be this. And then from here, you can have the loss of the propene to the 200, or you have the loss of the propene to the 218, followed by the water loss. Yeah, so that's the 200. The 183 is indeed the water loss from the 201, which is formed by the cleavage of the bond and the loss of the isopropylamine. Yeah, so that's the 201, because that would be the only way to explain, because from this you cannot have the loss of ammonia anymore. So you cannot go to the 183. And normally I say to the people, well, did you notice there's this 201 peak? Nobody did. You are the first to actually see that. I like that. Especially on this last course, which I do for Bioforum. It's nice that we have something really special. Thank you. Yeah. So that's what we have. Any questions on this? If not, let's move on to number 5.
I can try this.
Yes, please.
So I think if I calculated correctly, 7 for the top figure, 72 and 148 are the 2 complementary ions when you break the peptide bond between carbon and nitrogen.
Yeah. So up here.
Sorry. Yes.
Yeah. Okay.
And 219 is M plus H, and consequently 201 is loss of water. I guess from the yeah, I don't know actually from there, from where.
Yeah, well, the 201 is a loss of water, and that could be come from there. It could come from there. These are the most likely sites, and maybe it's a mixture of the two. You don't know. I generally say the loss of water is not very informative, because you see losses of water from alcohols, from aldehydes, from ketones, from carboxylic acids, and I've actually some examples where I see water losses from ethers. So water loss is not very informative. So we just state, oh, it's a water loss. Now, done.
Cool. And for the bottom part, the same strategy basically is 90 and 130 are complementary ions. Again, the cleavage of the peptide bond. And 201 is a loss of water. And 102 seems like to be a loss of C2H4 from 130.
If you say I have the cleavage at the peptide bond,
Right.
and I explain the 90 and the 130,
On the right, yes.
Yeah, then I would expect that the 102 is actually the CO loss from the 130.
Okay. Yes.
Which is more likely than getting a loss of C2H4, because then we have to take that out from the middle of the molecule, and that's not very likely.
I see.
Yeah. And in peptide fragmentation, that would mean that the 102 is actually a A fragment, whereas the 130 is the B fragment. I don't know if you are familiar with the nomenclature of that fragmentation, but this is clear. And the fun of these two spectra is that you see that you have basically the spectra from 2 isomers where you just interchanged the sequence of the amino acid, and from the spectra you can derive what is the sequence. So you can extrapolate from this result that for a larger peptide you should also be able to get sequence information.
Yeah, seeing the terminals. Right.
Exactly. Okay, then we can move to the last one. where I helped you a little bit by giving the elemental composition there. So is there anyone who wants to try?
Matt, I can try. The first cleavage happened between O and C. The right C and went with the mass 3.
It's
This,
difficult to
we
hear what
have
you say,
the-
Anna. Can you take the microphone a bit closer to your mouth, perhaps?
Okay.
No, we have some breaks from Anna. Maybe her Wi-Fi or internet is a bit slower, causing some breaks.
Yeah. Perhaps.
Okay.
Is there anyone else who wants to take the lead? Anna, if
If
you can
not-
hear us, maybe try to reconnect. Okay,
And
now we see you
unmute.
good. Now it's good.
Good.
Yeah, now
Yeah,
it's good.
that's
Okay.
Okay. Okay. I think that I have cleavage between in the right side between O and carbon.
So like
And
this.
Yes,
Yeah.
yes. And this in the second position between N and carbon. And yes, in this position, and this fragment, I don't know, have a mass 193, and after that, I have one fragment with mass 125 and fragment 669, I suppose.
Yeah. If I would cut the nitrogen carbon bond
Yes.
and I keep the charge at the bottom, so I get hydrogen rearrangement, of course, then I get the 69. That's
Yes.
the protonated imidazole. Yeah. If I have the cleavage here and keep the charge at this side, so I get the chlorobenzyl cation, that's the 125.
Yes.
And I know it must be this one.
Yes.
So this, because in the isoconazole, where I have 2 chlorines, I actually have a 34 shift relative to the 125. So indicating that it must involve this group and not that, because that one is the same for the 2 molecules. Yeah.
Yes.
And then we have the 193. And if I understand you correctly,
It's summary this.
Exactly. So you basically would like to combine the imidazole and the benzyl.
Yes.
Which would mean, in terms of the way we discussed about that in our previous session, it would be a skeletal rearrangement.
Yes.
Where you see the rearrangement of the benzyl group from the oxygen, most likely to one of the nitrogens of the imidazole. And what you kick out is all that.
Yes.
Yeah. And that is consistent with the elemental composition. So there's no reason to think it's going otherwise. Yeah, so that's actually what we see. So we see a skeletal rearrangement where the chlorobenzyl combines with the imidazole, and accurate mass indicates that this is what is happening. And we have seen benzyl rearrangements do occur. So this is a nice example where we see this. And I like your solution, yeah, because it's also my solution.
I just I suppose that we didn't see a fragment with the mass 188 because it's maybe too stable. And
what would be the fragment with 188?
No, it's a fragment. No, sorry. No, sorry.
Okay. So if there are no further questions on this one, I think we will have our break now, and then in 10 minutes we'll reconvene and start with the first presentation of today. Yep.
So it's now 10:40 around here, or 9:40 around your Netherlands. We'll meet in about 10 minutes. Make recording.
Okay, not everybody is back yet, but they will soon come, I presume. So let me start with the first presentation of today after discussing the exercises. And in this session, we basically look at, you could say, 3 compound classes. That is compounds with sulfur and sulfone sulfoxide, compounds with halogens, and compounds with nitro groups. And we basically explore the fragmentation for these type of compounds. And we start with sulfur compounds. If you have thiols, thioethers, and thioesters, you basically get the same type of fragmentation which you get with oxygen analogs. So cleavage on either side of the sulfur with charge retention on either side, hydrogen rearrangement, and so on and so forth, as we have discussed. The other group of compounds I will be discussing about, and there are of course far more sulfur compounds, but I made some choices and some limitations, are various sulfonamides. And there's some interesting thing going on, because quite a number of sulfonamide antibiotics, which are synthetic antibiotics, which are widely used, have been studied. And interestingly enough, these sulfonamide antibiotics show somewhat different fragmentation from many other sulfonamides. So one of the things which we see if we have aromatic sulfonamide with an alkyl substituent is that we see the losses of the SO2 with the alkyl. That means that the resulting fragment is an odd electron ion. The same you see if you have aromatic at both sides. So you can see the odd electron fragment after the loss of the aryl SO2 dot radical. But now you can also have charge retention at this side, so you get the aryl SO2 plus. And we will see some examples of that in this particular page, where we look at some compounds. There are some antiviral drugs, there are some anti-epileptic drugs, where you see these typical characteristics which we see, where we have losses of the alkyl as a radical here, as a radical here, and similar features like that. If we have sulfonamide antibiotics situation is a little bit different. I will come back to that later on. And if we have sulfonamide like this, we can actually see losses of ammonia. We can see losses of the HSO2 NH2, and we can see, so perhaps this is a combination of a loss of ammonia and SO2, and we see the H2N SO plus fragment with an M/Z of 80. And an example where we see this is this anti-epileptic drug, where we see this fragment 90. We see the loss of ammonia. We also see the loss of this group, but it's not immediately clear from the spectrum that it is this group, because it's actually something which is combined after the loss of the acetyl from the N-acetyl substituent there. But this is basically what we have in these type of situations. A special class of sulfonamides, you could say, are sulfonylureas, and sulfonylureas can have various cleavages. So immediately at the sulfur with charge retention at that side, it can have cleavage of the carbonyl nitrogen bond at the side of the sulfur with charge retention on either side, and it can have cleavage of the amide bond in the other amide bond in the urea structure with charge retention on the nitrogen side of the molecule. And there are some examples here for positive ion mode where you actually see this happening. Some of these fragments do occur. And one of the interesting things in studying the spectra of especially these type of or many other compounds from this class in a little bit more detail, that at a certain stage you can have the cleavage of this bond. So you produce the product ion 261. And in the spectrum, you also see a product ion 218, where the accurate M/Z actually indicates that the elemental composition must be consistent with the loss of HNCO from the 261. So you actually have a skeletal rearrangement where the nitrogen is combined with the sulfur, and you see the loss of the HNCO either from this or that. Of course, I don't know. I can't tell. And that's something which we see quite often in these type of structures. Okay, let's now move to the sulfonamides. And you may remember that we already discussed about the fragmentation of a sulfonamide, because we were looking at this spectrum in one of the exercise series which we had. So we have cleavage on either side of the sulfone with charge retention on either side. And a typical example which I want to discuss in this particular session is the sulfametazine or sulfidimidine, two names for the same compounds, which basically can show cleavage at this side of the sulfonyl, leading to the M/Z 92 and the M/Z M+H minus 93. So this one, that is the 186 and the 92. And we know this will be a direct cleavage, so they add up to M+H minus 1. We get cleavage at the other side of the sulfone with charge retention on the sulfur side with the 156, and hydrogen rearrangement and charge retention on the other side, which in this particular case is the 124. And you can say the 92 and the 156 are group specific fragments, because you always have this aniline group in, and the compound specific is depending on what is actually sitting there. And with the sulfamethoxazole from the exercise, we also looked at the product ion 108, which is due to secondary fragmentation of 156 with a rearrangement and the loss of and the loss of SO. And we also looked into the loss of 66 from the M+H, being the loss of H2SO2. And this is something which we see. And here is a proposed fragmentation, so basically a proposed rearrangement where we see the losses of the SO2 and the losses of SO from the 156 to the 92 and the 108 respectively. The loss of 66, so the H2SO2, is something which we see for these sulfonamide antibiotics in positive ion mode. And you can also analyze these compounds in negative ion mode. And in negative ion mode, you actually see the loss of 64. So you see the loss of SO2. And as I indicated before, MS to the power 3 data suggest that the phenyl ring, so from the aniline and the R group, are actually reconnected via a nitrogen link, as I proposed for the structure for the sulfamethoxazole, like this. So one of the things I do is I, especially in the early days of building this course, I was just screening literature for MSMS spectra. And at a certain stage, I found an MSMS spectrum of exactly the same compound, so the sulfametazine, which was acquired on an ion trap. And then I said, well, I have explanation for what is going on in the collision cell CID. Let's see if we can explore and see whether we see the same. And that, yes, we see the 186. We have some indication that there might be some 92, but we know the trapping of ions with M/Z values below 30% of the precursor ion is difficult in the ion trap. So that's why we don't see it clearly. We see the 156. We see the 124. There's some indication of a 108 there. But of course, our attention is immediately drawn by the fact that we see a 174. We see a 204. We see a 218. And when I see these weird things, and these are very old data, so there were no accurate mass data available yet, is I start trying to calculate, and I will calculate the possible elemental compositions for the loss of 75, which is basically from the 279 to the 204, from so the loss of 75 based on the elemental composition of a original compound. And I get a number of possible elemental compositions in my calculations. And what I then do is try to see if any of these elemental compositions can be taken out from the molecule in a logical way. And quite often this procedure leads me to an idea of what's going on, but in this particular case, it didn't. But then I realized, hey, we have an ion trap. And you should be aware of the fact that the vacuum system of your tandem quadrupole is saturated with mobile phase vapors, among which there's water. So you could imagine that the 186 being basically this ion with the SO2 here in the gas phase meets a water molecule. Yeah. So what is actually happening is we have this, it meets a water molecule and combines to produce a protonated sulfonic acid. Yeah, and that would explain the 204 as well as the 174. And when instead of combining with water, it would combine with the methanol, it gives you the 218. And later on, when ion trap was combined with orbitrap, we could actually see that the elemental composition of the 204 is actually consistent with this explanation. So what we can actually see in the ion trap, because of the long residence time of the ions in the ion trap compared to the collision cell, are solvent adducts of ions. Especially water adducts is something which I frequently see under these situations. So we see it with these type of ions. We can also see it in some cases with acylium oxonium ions that they, for instance, as a result of fragmentation of an amide or a ester, and it's picking up water as well. And sometimes you see these type of adducts in other situations. And in fact, my initial idea from having solvent adducts in this particular case come from the fact that I once had a molecule which a mass of M/Z 150, which showed in the ion trap a product ion with 174. And this product ion can actually be explained as being the loss of ammonia and the solvent adduct with acetonitrile. And then we changed mobile phase, so we removed the acetonitrile and put in the methanol, and then you don't see the adduct. Well, before we changed the mobile phase, we actually did MSMS on the 174, and we saw the loss of acetonitrile. So these solvent adducts occur. And if you use an ion trap, you have to be aware of the fact that these are there. And this is a good example to show this what is going on. For the solver, I have 2 more spectra and 2 more compound classes. And for the first of the 2, I actually move to the negative ion mode, and I look at TRC, the diuretics. And TRC diuretics basically look like this, and they have different side chains on the molecule, and sometimes they have a chlorine, sometimes they don't have a chlorine, and so on and so forth. So in this particular case, we look at the spectrum of this particular compound, but the fragmentation is basically similar as we always see. So we can, at a certain stage, get the loss of this whole side chain, and followed by losses of SO2 from there to the 205. And a very characteristic ion is actually this 287 ion, which is the M/Z value actually depends on the side chain, and it is consistent with the loss of 91, which is the combination of an SO2 and a HCN, so hydrogen cyanide. And the only way to explain this loss would be that you have the rearrangement of the R group here to either the nitrogen or the carbon here. And the way I wrote it is that it is going to the nitrogen, but very recently I saw some data suggesting that it might also go to this position. Yeah, this is something with. So again, we have an example of skeletal rearrangement. The last example is from a organophosphorothioate. And in the spectra of these thioates, you basically have 3 regions in the spectrum. You have the high end of the spectrum, where you see losses from the ester, which you have here. So we see losses of C2H4, C2H4, and water. At the low end, we basically see fragments due to the cleavage of the phosphor-oxygen bond and secondary fragmentation of that. And that these are the ions here. And in the middle mass range, we actually see, for all these organophosphorothioates, we see 2 fragment ions with an MOV difference of 60. And the 153 is very easily explained, because if you cut the bond, do hydrogen rearrangement, keep the charge at the ring side, you actually have the 153. So the 169 is 16 higher, suggesting that you now have a sulfur instead of an oxygen. And accurate mass tells you that this so-called Thiono-Thiolo rearrangement actually occurs. And sometimes I say, well, what we have is, upon fragmentation, we do some wheel of fortune here. And for some fragments, it's the CO. For some other fragments, it's the CS. And of course, it's something weird what is going on here. But you see it with a whole variety of compounds. It's confirmed by accurate mass. So this is just another example where we see unusual fragmentation with sulfur. And I feel that I always have to warn you that if you have sulfur, you can have these type of things. Okay.
Just to stop you, to make this clear. So in this case, the sulfur is getting the place of the oxygen?
Yes, it is.
On the hydroxyl, okay.
So what basically what you lose is the PO3 with its two side chains, instead of losing the PO2S, which you would lose here, because to make the 153, you basically cut the phosphor-oxygen bond, have hydrogen rearrangement to the oxygen and the charge at that side. Apparently, it's also possible that these two interchange, and you get the cleavage of the same bond then with the sulfur here and produce this. And it's very characteristic that the 169, or the ion with the sulfur, generally is a little bit more abundant than the ion with the oxygen.
And because that's the negative ion mode, right? And it's more.
No, this is the positive ion mode.
Oh, okay.
Because there's no negative here. Negative is there if I have negative in the heading.
Oh,
This is positive ion mode. These are pluses all the time.
So you are by default positive. Okay, that's good.
Yeah.
But in that case, there are also some other atom rearrangement, not just hydrogen. Basically, other atom types can rearrange in that case.
Yeah, but we have seen not only hydrogen rearrangement, but we have also seen rearrangement of larger groups. We have seen dichlorobenzyl rearrangements in the last exercise which we did.
Yeah. Yeah, but in terms of atom hopping, okay. Thank you.
In terms of atom, it's yeah. Okay. So let's move to the second part of this. And the second part is on compounds with halogens. And if you have alkyl halogens, so the halogen is on an aliphatic side, you can see primary and secondary losses of HF, HCl, or HBr. I don't have any examples for HI, so I can't tell, but most likely that will happen again. And perhaps I should explain the term primary and secondary losses. With the primary, I mean that you see the loss of HF or the HCl or HBr directly from the M+H. In the secondary, you see the loss from a fragment. So it can be a secondary loss, but it may also be a quaternary loss. So after two other losses. Yeah, that's what I mean. And so if it does not immediately come from the M+H, I call it a secondary loss. Interestingly, there are quite a number of steroids, anabolic steroids, which have some fluorine on the 6th position or on some other position, 6th position, or the let me say the 9th position. And for these fluorosteroids, you see losses of HF preceding the loss of water. So you first see the loss of HF, and then you see the loss of H2O. And if you would look in negative ion mode, it is the other way around. Okay. There's quite a lot of things to tell about halogens sitting on aromatic rings. First of all, you have to be aware of the fact that in quite many spectra of aromatic halogenated compounds, you don't see any fragmentation related to losses of halogens. So sometimes you do, sometimes you don't. Yeah. If you see losses, you will be able to see losses of HF, and you will see a competition between the loss of HCl and Cl dot, HBr and Br dot, HI and I dot. I have no examples where I see F dot losses. There is a higher tendency basically in the series. So I dot is lost more readily than Br dot is more lost readily than Cl dot, and F dot is not lost at all. Interestingly enough, the radical losses occur at lower collision energy, while in fact you would expect that since this is a homolytic cleavage, it will go at higher collision energy. But if you think about it, you can immediately explain why the radical loss occurs at a lower collision energy. That is, for the radical loss, you only have to cut one bond. Whereas for the loss of HCl, you have to cut two bonds because you have to take a hydrogen from somewhere. And obviously, it's not always readily explainable how you get the additional hydrogen for the HCl loss if the Cl is sitting on the aromatic ring. These losses, both the molecules and the radicals, can be both or either primary or secondary losses. The product ions which you see are generally not very abundant. So they are there, but not the major peaks in the spectrum. This whole story basically holds for both positive and negative ion mode. And if you have compounds with both fluorine and chlorine, you see that in the positive ion mode, the loss of HCl is predominant, whereas in negative ion mode, the loss of HF is predominant. These are interesting things to think about. And if you have aromatic halogenated compound with bromine or iodide, you can, in negative ion mode, also see the M/C 7981 for the Br minus, or the M/C 127 for the I minus. Yeah, and we will see some examples of this all in the examples to follow. But before we move to that, I have a separate box for compounds with trifluoromethyl groups. And trifluoromethyl groups are often put into drugs in order to basically avoid some undesirable metabolism. So there are quite some drugs where we have trifluoromethyl substituents on the aromatic ring. And what we can see from these are multiple consecutive losses of HF from the aromatic trifluoromethyl. And if you think about that, you immediately say, well, it will probably be difficult to propose structures for that. And I will show you examples of that. In addition to HF losses, in some cases you see losses of CF3 radicals, or you see losses of 50 CF2 involving a fluorine rearrangement to the ring. So you go from a difluoromethyl aromatic to a fluoroaromatic structure. Yeah. So let's go into some examples. We already, I already showed you in a previous session the spectra of some chlorophenols in negative ion mode, which all show basically primary losses of HCl. And here in this compound, you also have the example of a primary loss as well as a secondary loss, but a primary loss of HBr. You don't see radical losses in this particular case. So this is a aromatic compound with a trifluoromethyl substituent, and I actually have two examples, one in positive ion mode and one in negative ion mode, where we basically get a fragmentation. So what we first see is some cleavage from the piperazine ring, and then from the M/Z 188 in positive ion mode, we see two subsequent losses of HF to 168 and 148. And I can propose structures for that. If I would also have the 128, I have some problems. You should be aware of the fact that the loss of 20 is very characteristic for the presence of a fluorine, because there's no other way you can see losses of 20. As I said yesterday, we can, in some rare cases, see losses of 1 or of 2. The next loss is 15, which is the methyl. We can have losses of 16, of 17, of 18, of 20 due to fluorine. And then the next loss is 26, which would be the acetylene. And all the other values in between, which I didn't mention, are not possible. So for the negative ion mode, we basically have the same story, the same situation, where we have side chains losses from here, and then at a certain stage we see this series of HF losses. And I can still propose structures for the first and the second, but I don't know how to propose a structure for the third one, because frequently you see this in highly aromatic compounds where it's not easy to imagine the loss of HF. So perhaps you have to take some things apart to deal with that. But perhaps it's all, even not even necessary to propose a structure to see this. Yesterday we looked at the fragmentation around the nitrogen of the bromhexane, looking at the spectra where we fragmented the 375. So what I now will do is, instead of the 375, which is the 79 bromine 2, I will now fragment the 377, which is the isotopomer with the 179 and 181 bromine. And the spectrum which you get is shown here. And yesterday we had 114 and 262, but now of course we have 264 because one of the two bromines is an 81 bromine. We still have the 83, but from the 264, we actually see losses of Br dot, which could be the loss of 79 Br dot to the 185, or the loss of the 81 bromine to the 183. And the 183 and the 185, based on this structure with one nitrogen and the loss of the Br dot, these are odd electron ions, consistent with the nitrogen rule. Sometimes I say the greatest fulfillment of life of an odd electron ion is the loss of a radical. So what we actually see from the 183 and the 185 are losses of B dot. And from the 185, we can only see the loss of 81 bromine to the 104. For the 183, we can only see the loss of the 79 bromine to the 104. So the 104 is this structure with two B dots off. So it's probably challenging to write a nice structure for that. Perhaps you have to some four-membered ring or so. But it's an even electron ion again, because we have an even M over Z and one nitrogen. Yeah. So in this particular case, we see the B dot losses. It's nice and interesting that I can go back to all kinds of exercises and things which we done in the past, because we also looked at this particular compound at a certain stage, and this is the 2,4-D. And we already explained the 161 being the cleavage of the aromatic aliphatic ether bond to produce the 161, which is the dichlorophenoxy anion. This 161 actually gives two subsequent losses of HCl. And we have C6H3CO2O, from which we have two HCl losses. So the only way I can propose structures for this, that is without putting additional double bonds in the aromatic ring, is by opening the ring and propose structures like this. And this is something which you frequently see if you go down and down and down, and at a certain stage you end up with structures where it's with product lines where it's difficult to propose useful structures for. And this is a good example of that. And as you can see, these are only minor peaks in the spectrum, but they are there. Another example which we studied earlier is the fragmentation of the benzodiazone. And we basically looked at 4 fragments due to cleavages on either side of the carbonyl and charge retention on either side. Well, from these fragments containing the iodine, we can see losses of I dot and another I dot, or in this particular case, we only see one of the ions, we don't see the other one. And that's because that's probably below the range where we acquired the spectrum. And this is something which we see, so we see the I dot losses. Well, then probably we also need to have an example where we have both losses of I dot and HI, and that is something which we see in the fragmentation of iopromide. Iopromide is a X-ray contrast agent, so which is used if you want to have more contrast in clinical diagnostics. And basically, it's an interesting structure with some amide bonds attached to an aromatic ring with 3 iodines in it. And of course, you have to be aware of the negative mass defects which you have, because these are substantial with having iodine. And I have named the various side chains as being A, B, and C. And what we actually will see are losses of A or losses of B. And we see some fragmentation in the C, but we don't see the cleavage of this amide bond. So if we go into detail into the spectrum, what you basically see is either the loss of the A group, like this, or of the B group, like this. And because we have a N methyl here and not Here, you see the two peaks, which 14 units difference here. And from these two ions, you can have a variety of secondary fragmentation along 3 pathways. So what we can see from the 701 and the 687 are losses of 1 or 2 HI molecules to the 4 MOVD values indicated. We can see losses of CO and I dot to the 2 odd electron ions shown here. Or we can see losses of HI and methoxy, and the methoxy is coming from the C ring to 542 and 528. And of course, in this particular case, you cannot be completely sure whether you have loss of HI and the methoxy radical, or perhaps loss of methanol and the I radical. So the I dot. But in this way, you can nicely explain the fragmentation which is going on. And this is a complex picture of what is going on, but it's still doable, explainable to do so. Okay. I hope you understand that if you want to further look into all these type of fragmentations which we have here, you need basically after the course study more and look at the examples and so on and so forth. And sometimes I say we have the course now and it ends in some time after now, and then actually the actual work starts, because you will be applying what I have told you in practice. So the third group of compounds I'm looking at in this particular case are aromatic nitro compounds. And aromatic nitro compounds can actually show a series of losses, which is losses of hydroxyl radicals, OH dot, so losses of 70. It can show losses of nitrosyl radicals, NO dot, loss of 30. It can show losses of nitroxyl, which is basically HNO, loss of 31. It can show losses of nitryl radicals, which would be the NO2 dot, the loss of 46. And it can show losses of deoxo lambda 5 azan or nitrous acid, but since I'm not working in the liquid phase, I prefer not to use the name acid in the name of a neutral loss, which we see. I also talked about hydrogen cyanide or hydrogen isocyanide earlier. This is the loss of 47. And of course, again, what we see is this is either the loss of the radical or the corresponding neutral molecule, the loss of the radical or the corresponding neutral molecule. Again, like with the chlorine, we see that the radical losses occur at lower collision energy, simply because we have to cut more bonds in order to do so. It is hopefully clear that if you have the losses of nitrosyl or nitroxyl, so the losses of NO dot or HNO, there must be a rearrangement in the molecule, because instead of the carbon nitrogen, you are creating a carbon oxygen bond, which allows you to do the loss of the NO dot or HNO. If your molecule supports a primary NO dot or NO2 dot loss, quite often you see a secondary radical loss. So there are, I've seen quite a series of compounds where they're both nitro groups and halogens. So then you see NO dot loss or NO2 dot loss followed by the loss of the Cl dot, for instance. Also, if you look into the fragmentation of aromatic nitro compounds with substituents in the 2 position, you can, especially in negative ion mode, see ortho effects, which allow you to see in negative ion mode losses of hydroxyl radicals, and in positive ion mode, sometimes losses of H2O, and that's when the group in the 2 position is actually a proton donor. And in looking into the fragmentation of a whole range of nitro compounds, which is something which I did last year as part of my keeping on doing science in the Corona lockdown period, which we had. I looked into a variety of compounds, and I noticed that there are some other steric effects which you can see, and I will show you an example of that when we proceed. And if you want to read more about that, that's the publication, which is both on halogen and nitro compounds. You should be aware of the fact that aromatic nitro compounds are frequently analyzed by atmospheric pressure chemical ionization. And if you do so in the APCI spectrum, so we don't do MSMS yet, we simply look in the MS spectrum under APCI conditions, you frequently see next to the M plus H a peak consistent with M plus H minus 30. And given what I told you, you would expect that the loss of 30 is actually due to the loss of NO dot. Well, in 1997 or so, one of my former colleagues approached me and said, well, I have this aromatic nitro compound, I do APCI, and I see this loss of 30 in the MS spectrum, and I did MSMS on the M plus H, and the M plus H minus 30, and assuming that the minus 30 is the loss of NO dot, I cannot explain at all what is going on in the fragmentation of the compound. And then in this time, I was working on editing a book, and one of the authors of the book was Yehuda Yinon, who was in those days head of the laboratory of the police department in Jerusalem, and he has a extreme high experience in looking at nitro compounds, and you immediately understand why that is. Police department nitro compounds explosive, then you immediately understand why this is. And he showed that under GCMS conditions in chemical ionization, what you actually see is not losses of NO dot, but a thermally induced reduction from the NO2 to the NH2. So I said to my former colleague, hey, this could be a possibility. Perhaps you should look into that. And he immediately responded, I tried this. Yes, this is what we see. And then there was this Czech group from the Czech Republic who did a very nice experiment to actually demonstrate that the thermally induced reduction also takes place under APCI conditions. So what they did is they did an HD experiment by replacing the water by D2O in the mobile phase. And since there is no exchangeable hydrogen in this particular case, for the M plus H, we now get the M plus D. And if the 294 would be due to the loss of the NO dot, you would now get 295, while in fact you see 297, indicating, consistent with the thermally induced reduction of the NO2 group to the NH2 group. And the reductive effect is more prominent if you have protic solvents. So it's more prominent in water methanol than it is in acetylnitrile. Yeah, so this is something which you have to be aware of if you look at these type of compounds. In one of our exercises, which we discussed yesterday, we had nimodipine, where we had these side chain losses and so on and so forth, and we nicely found out that in the end we see losses of NO2 dot from the 301 fragment ions, which we created by taking off the ester side chains. Well, the nimodipine is an example of what you could call a 3-nitro dehydropyridine. So in this particular case, we have the nitro group sitting on the 3 position. In the same class of dehydropyridines or dipines, as they are sometimes called, which are medication for the heart, we also have a number of compounds, among which is nifendipine, which do not have a 3-nitro substituent, but a 2-nitro substituent. And in the spectra of the 2-nitro substituent compounds, you actually see loss of the ester side chain, and then that is followed by the loss of CO2. And basically the only way I can explain the loss of CO2 is by assuming that upon the loss of methanol in this particular case, I get some ring from which I can take off the CO2, and in a similar way I can explain some of the other fragments which I see. And I'm not completely finished with this, because there's a lot of things which are going on, and I'm happy that I recently heard that another colleague of mine now has a PhD student who is looking into these type of fragmentations, trying to do some calculations, doing some lots of experiments. So this is something which we will learn about more. But what is important here is that we see that in some cases we can have interactions between groups which change fragmentation characteristics in MSMS. Okay. So since we are moving towards the end of the course, we have to clear our loose ends. And one of the loose ends is related to the loss of 46 from the nitrotyrosine. So let's look into this. And if we compare the spectrum of the nitrotyrosine with that of the tyrosine, we see in both cases we see the loss of 46, perhaps suggesting that in both cases we see the loss of formic acid. But of course we cannot be sure, because it might be that in the nitrotyrosine the loss of the NO2 dot is much easier. Another thing which we noted in both spectra are losses of ammonia followed by a loss of 42. And if I look at this structure, I cannot immediately propose a fragmentation which would lead to the loss of 42. So there are two things I want to explore. Is the 46 loss due to a loss of formic acid or NO2 dot? And how to explain the 42 loss, which most likely is CH2CO. Yeah, and of course, the loss of the 46 we could very easily explain by using accurate mass data, because if we would have the loss of formic acid, this would be the elemental composition, so this would be the accurate mass, or the exact mass actually, if we have the loss of the NO2 dot, we will get a different mass. So if we would acquire the spectrum on a QTOF or an Orbitrap, we can immediately tell what is going on. But in fact, what we are going to do is we are going to look at MSMS spectra of labeled substances. So we do a deuterium exchange experiment. We have labeling of the deuterium labeling of the three hydrogens on the aromatic ring, and we have a alpha-alpha D2 labeled substance. And finally, we have a 13C9, so a fully 13C labeled analog of the nitrotyrosine as well. And we use the data from this in order to sort out the two questions which we have. So if we want to find out what is the loss of the 46, whether this is loss of formic acid or the loss of NO2 dot, of course, we immediately start looking at the 13C9. And we see that we lose a carbon. So in fact, by doing this experiment, we have demonstrated that the loss of 46 is indeed the loss of formic acid and not the loss of NO2 dot. Because if it would be the NO2 dot loss, this would be a +9 instead of a +8. Yeah, we use some of the other data to explain the 42. And basically what we are going to do is set up a fragmentation scheme. So from the 227, the M+H, we see the loss of ammonia to the 210. And the loss and the ammonia is sitting on the beta hydrogen, beta carbon. So what I would actually expect to have charge and thus hydrogen rearrangement. So I would expect that the charge would rearrange from the beta position to the alpha position, because then it's better stabilized by the aromatic ring. So if we do so, we get an alternative structure for the 220, and for the alpha-alpha D2 labeled substances, that means that one of the deuteriums is actually moving to the beta carbon. If we now write this structure slightly different by closing the ring, we can actually see the loss of the ethanol, the CH2CO, so the C2H2O2, to get this 168 fragment ion. And if this mechanism as we proposed here would be correct, we would expect that the 168 fragment is having only one deuterium left in the alpha-alpha D2 labeled substances. And if we go back, we can see that this is actually the case. So in this particular case, we can use the information from the labeled substances to actually propose a mechanism for the loss of the 42. And that we have C2 losses is obviously also indicated by the 13C9 fragments. Okay, so we have solved this thing which we carried around since last Wednesday. Yeah. Okay, so I come to the end of this presentation, and now we have a slightly different procedure from what we had in all the other sessions, because we have a slightly longer break. Yeah, so it's 10 to 12 now, and we'll come back again at a 12:15, or for Sophia 11:15, because I want you to work on these two exercises. So you first take your 10 minutes break and you do all the exercises which you do all the time. And of course, you all switch off your camera, so I don't know if you actually do what I ask you to do. Walk around, get tea and coffee, and jump and shout, and so on and so forth. But then you have about 15 minutes or so to work on these two exercises. And there's another exercise in this set, but we will skip that, and you can look at that at a later stage. So we just concentrate on these two exercises. And I see you in 25 minutes for the last session. Is that okay with you?
So 12:15 or 11:15.
Yeah. Okay, then you have 15 minutes. I think that should be enough. Okay.
Yeah.
See you.
Good luck with the exercises.
Okay, the floor is yours. Can you explain the fragmentation? Did you have enough time? Did you need more time? What about? All very quiet.
I had some time to look at only the left example. So I can maybe try to go at it.
That would be nice.
So we see 172 is the m plus h, and then the difference to 128 is 44. That I speculated might be this hydroxyl side chain that is basically in.
So you cut here.
So yeah, that was. I guess that was the most probable explanation. So C2H4O.
Yeah. So what you actually do is you cut here. You get hydrogen rearrangement to the nitrogen, and then you keep the charge at the bottom. So
yeah, exactly. Thanks for giving the full explanation. And then basically we are left still with an even mass, which corresponds with the nitrogen rule. So we are still okay. And then the next fragment 82 is a mass difference of 46. So that, I guess, most reasonably corresponds with the loss of NO2 from the ring, but that means that basically 82 needs to be an odd electron, so radical. Yeah, but the loss of NO2 is not the loss of NO2, but it's always the loss of NO2 dot. So you lose a radical. Okay. So the 82 is indeed after this loss, the loss of NO2 dot from the 128. And then we can also explain the 45, which is basically the complementary ion to the 128, because these add up to 173, where the charge resides at the top part. So the same cleavage as we have for the 128, but now with the charge at the top part. Yes, and the whole ring is lost as a neutral loss. Exactly. And then we don't get nitrogens anymore. Okay, good. Exactly. So somebody else for the right spectrum? Thank you, Neil.
Yeah, I can try.
Yeah.
So first I cleaved CN bond to lose NH3 minus 17 for the fragment 294.
Yeah.
After this, I can lose instead next bond with carbon. So it will be loss of 29.
Yeah, that would be this loss.
Yes.
And you see the loss of the imine because you have the sp2 carbon here.
Yeah.
Yeah. So that's the 282.
And the next one will be loss of chlorine radical to produce of 259.
Yeah. So from the 294, we can see the loss of the Cl dot.
Yes. From 294, yes.
And if you have carefully look at the spectrum, you actually see that there's competition between the loss of the CL dot and the loss of the HCl, because there's a 258 here as well, which is consistent with the HCl loss from the 294. The peak
Okay.
in front of the 259.
Yes, yes. Mhm.
And you would expect that if you increase the collision energy, that the 258 will increase and the 259 will go down because of what I told. Okay, so we have the schemes which are there, clear. And the schemes will be in the handout, so that's something which we have. And also the story about the other exercise which you didn't do is in the handout. So thank you all for this. Let's go to our final session. And in the final session, we are going to do a couple of things. And I would like to start with, at a certain stage, I decided, let me try to write down what are the steps I take if I interpret an MSMS spectrum of a known or an expected structure. Yeah. So my starting point is the structure or proposed structure. And from this, I will actually predict expected bond cleavages based on the fragmentation rules I've developed. Yeah, and these fragmentation rules are summarized in the book, and I gave them to you during the course. In this, I can be helped by the tables with characteristic neutral losses or product ions, which I also provided to you and which are in the end of the manual. Then I calculate for the predicted fragments nominal M/Z values, and I check them against the spectrum. And if there are still ions left, I will use accurate M/Z data, if possible, to derive elemental compositions. And again, try to propose structures based on the fragmentation rules. And then I will check the interpretation which I have, so elemental composition of the various fragments, against the accurate M/Z values which I have available. And sometimes I use additional checks using M/Z shifts in stable isotope labeled compounds. So let me give an example of this. This is a tyrosine kinase inhibitor. It's an anti-cancer drug called afatinib, and the structure is given here. And if I look at the structure and I say I predict bond cleavages, I would expect that I have cleavage here with charge retention on either side. I would have a cleavage of the amide bond with charge retention on either side, and I would have possibly cleavage of this CO bond with charge retention primarily at the bottom side. And if I do so, and I have calculated the M/Z values, I basically have explained only 2 out of the fragments which are there. So it seems not to be very successful. But then I realized, of course, in addition to what I just said, I could also have combination of losses. So I could have, for instance, have the loss of the dimethylamine in combination with the loss of the 5-membered ring, or the cleavage of the amide bond in combination with the 5-membered ring. And if I do so, I explain 2 more peaks in the MSMS spectrum. And then I have the 343, which most likely is a CO loss from the 371, which actually can be done by easily be demonstrated by showing that the loss of the methylamine actually results in ring formation here, from which we can readily see the CO loss. So that's what we have. And then based on the structure, basically based on the fragmentation I just described, I calculate M/Z values. So exact M/Z values for the various product ions. And in this particular case, I had an ion trap, orbitrap MSMS spectrum of this compound available, which I could use to check accurate mass. And in the ion trap MSMS spectrum, you also see the 416 ion, and the 416 ion would be consistent with the just the loss of the 5-membered ring, something which we didn't see in the collision cell CRD. So basically, from the information which we have from the ion trap, we could confirm this fragmentation. And of course, in the ion trap, we don't see the 112 because that's way below the 30% of the M+H of the precursor ion. And we also don't see the M+H because in the ion trap, the M+H is in most cases completely fragmented. Yeah, and there are also some numbers, and this is done on the next page as well. For some of the fragments for labeled substances, we have some data, and these are consistent with the interpretation. This is something which I frequently check. Yeah, so that's one of the things which is important to deal with. Okay. In principle, you could also say, well, what I do is I acquire the accurate mass, and let's assume that we have an unknown. Yeah, and I have acquired an MSMS spectrum with an unknown, and I have a structure because in this particular case, I know what it is, but that's not important. I keep that out. So basically what I say is I have some prior knowledge because I know I only have carbon, hydrogen, nitrogen, and oxygen in. Yeah. So what I do is I start calculating elemental composition for all the ions. That is for the 239, which is the precursor ion, I only assume even electron ions. For the others, I calculate both even and odd electron ions. And the spectrum is acquired on an instrument which gives me a mass accuracy of 3 millidalton. Yeah. So what I'm going to do is I'm going to calculate possible elemental composition for all these ions. And I start by doing it for the precursor ion. And basically I get 6 hits. And then I say, oh, wait, all the hits where I have the RDBE, which is an integer, these will be odd electron ions. I produce an M+H, so I can remove them from the list. So I reduce my list. And in the same way, I calculate possible elemental compositions for all the product ions shown in the MSMS spectrum. Yeah. The next, and some of them are odd electrons, some of them are even electron ions. That's what I see. And the next step, what I will do is, because I have to find out which of the 3 precursor ions is actually the correct one. So what I do is actually start seeing whether this particular elemental composition can be taken from this. No, it cannot, because I cannot have a fragment with 10 carbons if I have only 7 in my molecule. It could come from this, it could come from that. And in the same way, I basically look whether these elemental composition could come from the elemental compositions I have calculated for my precursor ion. And when I do so, I see that for the first, I only have a few ions. I even have less possible product ions explained for the second. And it seems that I have a good explanation for what is going on with the third. So actually, based on this, I expect that the C11H19N4O2 is actually the most likely elemental composition of the precursor ion. So taking it into account that the product ions should come from the elemental composition of the precursor ion. And you realize that in some cases, especially when you do ion trap fragmentation, and you might have these adducts, these things might go a little bit wrong. And there is actually software available with the instrument software from some various instrument manufacturers, which actually perform this calculation, which I now did in as part of an Excel sheet. But these softwares are available, so this is something which you can do. And then you use the elemental composition of the product lines to get greater certainty of the elemental composition of your unknown. And that's basically what I wanted to show at this stage. And then I skip a few pages and move to this particular page, which I already showed you before, where we say we have different types of unknowns with different strategies. And sometimes I argued in the second session we had last Wednesday, these are not all unknowns, something like that. So now I would like to come to the last part of this page. And I will be discussing identification of unknowns. And basically, I discriminate between two types of unknowns. That is known unknowns and real unknowns. And perhaps you think known unknowns is a bit weird, but basically a known unknown is a compound which is unknown when I start looking at it, but the compound has been described, it's reported in literature, can be found on the internet. If it's not, then it's a real unknown. And unfortunately, I have to say that if something is a real unknown, the probability that you will succeed to convince yourself and other people that you have identified the compound, it will be difficult. And when I say so, I know lots of instrument manufacturers don't like my statement because they believe that they can do it. I say, in most cases, I can have different possible structures and I cannot even discriminate between these. I remember a situation that I was consulted by a company who, the water company in the Netherlands, who fished something out of one of the rivers, and they gave me some idea about what it could be, and I checked the fragmentation against this structure, and then I said, well, it could be a possible structure. And while I was looking at it, they did some NMR work, so they came up with an alternative structure. And in the same way, I could explain the fragmentation from this alternative structure. And so most likely the alternative structure was the correct one. So this is something which I will illustrate basically with two examples. And of course, the identification of unknowns is very important also in your line of work and the way you work. And ideally, what I would like to have is I would like to follow an identification procedure described as such. So I get M over Z with good mass accuracy using high resolution mass spectrometry, which I use to estimate possible elemental composition from this accurate M over Z. Then I will search compound databases to find possible structures for these elemental composition. And I will try to link, basically filter the structures I get based on the MSMS or MS to the power n data I get, and see what are possible candidates. And then I might need to buy some authentic standards or things like that, and so on. And this is the general procedure which is there, which I will illustrate. But in my first example, I actually used some data which were acquired in the laboratory, where they only have an ion trap available, and they had to go to a different department to get the high resolution data. So we start out with the ion trap data. And this is some unknown in a pharmaceutical formulation, and the unknown compound is actually not related to the active pharmaceutical ingredient. And the unknown was found in LC-UV analysis for routine checking of this compound in a QC lab, and the UV was acquired on a photodiode array detector and indicated the presence of a phenyl group in a molecule. The MS spectrum, which was subsequently acquired using a mobile phase with ammonium acetate, is this. And I can explain this spectrum in two ways. I can either have an M plus H of 212 showing a small ammonia loss, or I have an M plus H of 195 showing a huge ammoniated molecule, M plus NH4 plus. And in order not to start with two possibilities, I will bring in another LC system. And this LC system is actually running with TFA rather than ammonium acetate. And I will use the photodiode array to keep track of the actual unknown peak from the spectrum, because of course I will get different chromatographic conditions whether I have ammonium acetate and trifluoroacetate. And the reason for bringing in another LC system is TFA is sticking everywhere. So I don't want to have the TFA being used in all kinds of systems. I just want to have one LC system which is running on TFA. And when I perform the experiment,
Why not inject a negative mode?
No, I do positive ion mode. And of course, I don't do negative ion mode if I have TFA present.
No, I'm talking about in normal injection without TFA, just to inject a negative mode to see if you still have plus NH3 or not.
This is a possibility, but it was not done. So I don't have the data. And I expect you don't get data for the negative ion mode, but I cannot be sure because it hasn't been done. But that would be a good idea. Yeah, and I like doing both positive and negative ion mode, but most people stick to the positive ion mode. But from doing the experiment with the alternative mobile phase, we got the same spectrum. So we know we have a compound with a mass of 211. So we have an odd number of nitrogens. And we have the ion trap, so we can do MSMS. And we get the MSMS, we still see the loss of ammonia, and we get two product ions, 94 and 119, which actually could be two parts of the same molecule, complementary ions, because the sum of the MOZ values adds up to 213. Yeah, whether that's true, I don't know. So I want to have more. So since I have the ion trap, I can actually start building a fragmentation tree. So I can perform the MS3 experiment, which means that I acquire the MS2 spectrum, and subsequently I get the MS2 spectrum of the 195, of the 119, and the 94. This is what we see here. And then I can start interpreting the MS3 spectra. And if I start with the left one, I see a 94, which if it would be an even electron ion, would contain a nitrogen. And what we see is basically the loss of ammonia to 77. So indicating that the 94 is indeed containing a nitrogen. And the 77, if I would go to the table, which the tables I showed you, will most likely be the C6H5+, so the phenyl cation. And we know the phenyl group must be there from the UV data. So the 94 basically is protonated aniline. And in the same way, I start looking at the spectrum here. And what I see from the 119 is the loss of 27 to the 92. And the loss of 27 is, according to the table, the loss of HCN. This means that if the 94 and the 119 are complementary ions, the 119 must contain 2 nitrogens. Because of the nitrogen rule, because in total I must have 3. I must have an odd number. I have 1 here. I know I have 1 here, so there must be a second one. This means that the 77, probably most likely again a phenylcation, should actually be due to fragmentation directly from the 119, involving the loss of 42, which is the CH2N2 molecule like this. And then we basically come up with a whole story, and we can glue everything together and make a structure proposal, as we have done here. And from this structure proposal, I of course calculated the elemental composition and calculate the RDBE, which is consistent with what I show here. So the next step in the procedure is that I now want to confirm the elemental composition by accurate mass. And the accurate mass acquired on a time-of-flight instrument is 212.1196. And I consider the presence of carbon, hydrogen, nitrogen, oxygen, fluorine, and phosphor. From the isotope pattern in the spectrum, there are no indications for the presence of chlorine, bromine, sulfur, or perhaps silicium. Well, silicium is not very likely. So these are the boundaries I set, and I asked the program to calculate the elemental compositions. And please be aware of the fact that this is not the best program available. There are far more intelligent programs than this, but in this particular case, I get 17 hits and I use it. And then I start clearing the hits. First, I know I have produced an M+H because I was doing electrospray, so we can remove all odd electron ions from the list, which are all the ions which give you an RDBE of an integer value. So these are the blue lines. I know I have an aromatic ring present, so I should have an RDBE of at least 3.5. So I can remove any with lower RDBEs. And then I get the C13, H14, and 3, which I basically calculated from the interpretation of my MSMS spectrum. But I also have 3 more possibilities. That is one with fluorine, one with phosphor, and one with 2 fluorines. In the MSMS data, I didn't see any indication for presence of fluorine or phosphor, but that's not necessarily something which is there. So what I start doing now is basically I take these elemental compositions for these ions. I take off the hydrogen. So I move from the protonated molecule to the molecule. And these elemental compositions I start searching in compound databases like GemSpider or PubChem. And when I do so, I don't get any hits for the 2 compounds with the fluorine, nor for the compounds with the phosphor. And if I search the GemSpider database for C13, H13, and 3, I get 415 possible structures. And then I decided we will have time limitations, so we cannot go over the 415 different structures. So I decided to search another database, which is the Sigma Aldrich catalog. And I then always say, this has the advantage that in the right-hand corner of the screen, you get this button and you push on this button and you can, oh no. In my organization, of course, I need to fill out 5 forms before I can order a compound. I cannot immediately do that from the website, but okay. So the Sigma Aldrich catalog gives me 5 hits, and these are these 5 hits. So what I now start doing is, with my expertise on MSMS fragmentation, I start looking at these various structures and see whether I can explain the loss of ammonia, the formation of the 94 and the 119 product ion. And basically there are only 2 out of the 5 structures where I can explain all these features. Yeah, and of course you say, well, I'm not that experienced. So one of the things which you could do is, for instance, use Mars Frontier or some of these other fragmentation ion prediction softwares to see whether you can actually see these various fragment ions, and then compound number A comes out. But okay, I have 2 where I have explained, so I order both these. I inject them in the LC, check the MSMS spectra, check the retention time, and basically I found out that this is the most likely compound. So I will write a report and say that I have a structure proposal for this unknown, which fits to the elemental composition, derives from the accurate M over Z, which fits to the fragmentation which I see, and the data are consistent with an authentic structure, an authentic standard, which gave the same retention time and the same UV spectrum and the same MSMS spectra as well. And of course, I will never write, I have identified the compound, because all my statements are probability statements. I cannot be sure. You might think of another structure, which could also be possible. Yeah, so that's the way I do this. If nothing shows up from the database, or nothing shows up which would be consistent with the fragmentation, then you have to try to build something yourself. And the problem is that in principle, the amount of information which is present in these spectra is very limited. So that gives you one of the problems in getting unknowns. Quite often, you don't have enough information in the MSMS spectrum to really build a structure from scratch. And that's something which is always of concern, of course. So I would like to give you another example. And in fact, what I did is I took the propazine MSMS spectrum, now with the accurate M over Z data, as an example to go through the interpretation procedure again, step by step. And I will show what I was doing. So this is the spectrum, there are accurate mass, and actually you can see there are 2 ions here, which have 2 different elemental compositions. So these are isobars with different elemental compositions. So we have to look into that as such. So I start out by, I have a precursor ion. I don't know what the elemental composition is. I have seen from the MS spectrum that I have chlorine present, and there's 1 chlorine present. I take that into account. So I start doing the calculations for a number of carbons, hydrogens, nitrogens, oxygens, and 1 chlorine. This is the accurate mass I do. So I get a number of possible hits. Only 2 of these hits actually contain the chlorine. 1 being an odd electron ion, the other one being an even electron ion. So basically from this, I can conclude this must be the elemental composition. Yeah, and possibly the UV spectrum can give additional information. The ability to do both positive and negative, which doesn't work in this particular case because I get only data for positive ion mode. I use the information from the isotope pattern, and perhaps if this would be an unknown, I have additional information. Somebody has tried to do something, or and all this type of information should be taken into account. So in this particular case, I get just one elemental composition which fits all the criteria I've set and which fits to the data. So what I'm going to do is I'm going to take off the hydrogen and search the database for structures, and again use the GemSpider database. And the main reason is because I can nicely give the data in a very easy way, and I get in total 221 results hits for this elemental composition. And on this page, I actually show the first 20 hits. And if I look at these, I can say, well, this is ruled out because this is not C9H16 ClN5, but in fact C9H15 N5, because it's HCl salt of this particular compound. So the chlorine is not covalently attached, so I can rule that out. Yeah, so that's what I get. And of course, I have a whole variety of pages more, but I will not do that. So the first thing the next thing which I will do is start looking at some of the product ions which are there. So if I take some of the product ions which I have the 188. So I do elemental composition calculations for the 188, and I have to find something which fits within the elemental composition of the precursor ion. And from basically looking at what I get, I come to the conclusion that the correct elemental composition is this one, indicating the loss of propene, as we already said when we looked at the exercise of this one earlier. And the same I do for the 152 and for the 146. And each time I can get interpretation from that, because I have the elemental composition of the 188. I see the HCl loss to the 152. I see another propyl loss to from the 188 to the 146. So basically, I come to the conclusion that I have two C3H6 losses, consecutive C3H6 losses. So what I can do is I can start looking at the structures which I derived from the GemSpider database of the elemental composition and check whether it can show losses of 42. And this one can, this one can, this one can. None of the others on the first page can do that. And this is the second set, and none of these structures show losses of 42 as being propene. And the same holds for all the other hits which are there. None of these others actually give this two propene losses from their structure. So basically, in this particular case, I'm stuck with only three different possible structures which are there, which is the propacine, the analog where you have two propyl chains on one nitrogen, and the analog where you have two propyl instead of isopropyl on both these nitrogens. Discrimination between these three structures based on MSMS data is impossible. And propyl and isopropyl substituents cannot be distinguished. But of course, what we could do is run these compounds in GCMS, because under GCMS conditions, we will have a difference in fragmentation between at least this compound and the other two. And then, of course, if we have standards, we can do LC analysis. We can do NMR analysis, perhaps, if we would have enough material, which certainly is not always the case. This is something which we can do. And we can also look at the other ions which are in the MS spectrum, and basically start calculating possible elemental composition for these ions, which allows us in the end to set up a fragmentation scheme for the propazine, where we basically have two proposals, so two different isobars for the 152, and two proposals, two isobars for the 110, consistent with the data which we have. So this is another example where I take more into account the fragmentation and combining various features which I was outlining in this presentation. Which brings me to the end of the story. And I can, well,
Can I ask
any
a
questions?
question?
Yeah,
Yeah.
of course.
For the last example, I mean, a critical step was to take the 220 structures that came up of Kim spider and to end up with only 3 probable due to the particular loss. So did you actually manually go over these hundreds of structures, or maybe
I looked at all of them, yes.
Okay.
And of course, the loss of the propyl or isopropyl as a propene is something which I can readily recognize in this particular case. In some other cases, it will not be that easy to say, hey, oh, I can rule out this possibility.
My question is it are there some programs like Mass Frontier that can treat in batch structures? I mean, not to introduce, for example, another option, just to introduce each structure to Mass Frontier and just to look on the neutral losses, which of them gives loss of propyl, like you do it on by.
Yeah, that would be a possibility. And there are software workflows, partly under development, partly available, which actually do this type of things. And you will, in your work, need far more of these strategies, more advanced strategies, in order to do so. But I don't have access to these software, so I have to simulate what that will do.
But can you maybe suggest us these softwares maybe we can buy or to find?
No, I know there are a lot of developments going on, but these developments are going too fast, and since I don't have access to these softwares, I cannot say check the quality of these softwares.
Okay.
So you mentioned Mass Frontier. Mass Frontier is a very nice package. It's very powerful, but it's also making some predictions of fragmentation which I never see. So one of the things I've noticed, that if you have a carbonyl in your structure, the Mass Frontier predicts that you will see the loss of 16, the loss of O. And from the thousands of spectra I've interpreted over the years, I've never seen this. And I expect that if I would interpret another million spectra, I will still not see it, because I think this is not a possible fragmentation. So these softwares are useful, but they do not give you the final answer. You will have to put in your intelligence, and in some cases, you will not be able to get a definitive answer. These are tools to help you not to make decisions. And this is something which is important to realize. In all software, it's just a calculator, and you have to make the decisions. If there are no further questions, I would like to thank you all for being with me during
Sorry,
these.
can I stop you just a moment?
Thank you.
Hello, is there somebody else?
Yeah. Anyone has some other questions? Otherwise, I really want to thank our dear friend, Professor Niessen, for his last course in Bioform. I believe that more than 20 years we are working together, and I really don't know what to say and how to thank him. But I believe that you enjoyed the course and benefited from it. And it really concludes the, I believe more than 15 courses. I don't know, I never counted them.
27.
That, how many?
I did 27 courses with you.
27, Yofi,
Yeah.
Wonderful. And you
Since
know what is Yofi?
since 1998.
1990, more than 20 years, as I say.
Yeah. Exactly.
We enjoyed it. I was on your course almost all day long. I enjoyed it. Thank you. I don't know what to say unless thank you, and see you in Israel as our guest, not as our lecturer. And,
We'll see what when that will be possible again, because
yes, of course. And thank you, all the participants. And I will be happy to keep in touch with you. Thank you again.
Yeah.
And on behalf of me, God, and all the staff, of course, Amir, thank you so much, Professor Niessen. I don't have anything else to add.
No. Okay.
God, what you say are you there, God, to say some words?
I'd like to first thank all the participants for their participation in the course, and hope that they have learned something and have a lot of things to continue thinking about, because I always say course is nice, but the real work starts after the course, because then you have to apply these things. That's something that it's clearly there. And of course, I would also like to thank Bioforum, you, Yehudit, Gat, and Amir in the very early days for the confidence they had in me to run courses. And I always liked doing that. And I can say, and I can say to you, I was enjoying myself in doing the course, and I always have some difficulty in hiding that. So I hope it has been useful. So perhaps we see each other or have contact in other ways. Bye.
Bye.
Will you be available
Bye-bye.
by
Thank
email
you.
for some questions?
Thank you very much.
Thank you very much.
Did you hear me, Wilfried?
Please repeat, Stan.
I guess because the course was very intense, and basically enough material for a semester was given in less than 2 weeks. So I guess many questions will come up, at least from my side, probably from Ilana's. Will you be available by email for some particular topics? Or is that
My email address is in the front of the course
Okay.
manual.
Mhm.
But you should be aware of the fact that I'm retiring, and for me that will actually mean that I will leave the field. So you can try, but you should be and sending me a message, and the email address will be active for some time. But at some point I might decide I don't want to reply to you. Well, I will reply that I will not have the priority to deal with your questions anymore.
Okay, we'll try to be quick. And some technical issue that some diagrams, particular fragmentation diagrams, were not included in our handout in the PDF. I think you mentioned it in the beginning. That maybe some updated version can be sent, or some addendum.
When everything is correct, you received handouts in relation to the exercises, and you will receive 2 more. They were sent to you by Gat via the email, and basically the things I show in the as part of the discussion of the exercises, these are all in the handouts.
But also throughout the lectures, there were like here and there, like a few more explanations with structures that Okay, it's not critical, I guess, but I just,
Yeah,
was
well,
just wondering if
if there
something more
is
updated.
if there is I don't think there are too many of these which are not in the handouts, but because I try to put as much of the things I add into the handouts, and sometimes of course I also repeat pages which I showed in a previous session, which might also, you might not remember that, but so I just copied them in.
Okay, good.
Yeah.
Thanks.
But if there are some questions, please.
Yes, I have
ask
another
that.
question. Once more about natural products. As I understood, you don't have something published about natural products, but maybe you have some, I don't know, some slides or something that can help us, because this course is great, but natural products sometimes they have specific rules per groups of compounds as well. And this is crucial for us. So if you have something, you can help us.
I remember having found at a certain stage a paper which gives some more detailed interpretation of some natural products. So fragmentation of some natural products. There are some additional things which are not in this course. So that might be useful for you. And what I will do is I will try to locate it and have it sent to you all as a handout from by God's later on today.
Oh, it will be great. Thank you.
Yeah. Okay.
Will be great.
So bye to all you, and you never know when we see each other again. World
Thank
is
you.
small.
All the best.
Yes. Bye.
Thank you very much.
Thank you very much.
Thank you very much.
Bye bye.
Cheers.
Ciao.